I have selected today's topic of discussion, that is uh, the velocity triangle of centrifugal pump. In this series of centrifugal pump, I have already covered the working principle of centrifugal pump. The velocity triangle is in continuation of this series. Based on my experience, I would say that the velocity triangle is very important topics if you want to understand the full concept of design of centrifugal pump. I suggest you should also understand the velocity triangle. In centrifugal pump, slip factor or slip phenomena occurs at impeller outlet, and so there will be two outlet velocity triangle, one for ideal case without consideration of slip factor and another for real case or actual case with consideration of the slip factor. Velocity triangle for ideal case is shown as a dotted lines, whereas actual case it is shown as a solid lines. One more information I would like to tell you that drawing for drawing the velocity triangle, it is not necessary to draw the image of impeller. However, here I have shown the image of impeller also for better understanding. Drawing the velocity triangle is tricky, and so I have made in various steps for construction. In centrifugal pump, as flow of fluid is in axial direction, the inlet velocity triangle is drawn at inlet mean blade height unless otherwise stated. Please note that there could be many inlet velocity triangle at different inlet blade height, but inlet velocity triangle is drawn at inlet mean blade position. So let's start construction of velocity triangle. Before that, important velocity terms: inlet mean impeller velocity u1, inlet mean relative velocity v1, inlet mean absolute velocity c1, inlet mean whirl velocity cw1, inlet mean axial velocity ca1, inlet mean blade angle with respect to axial beta 1, in outlet velocity impeller velocity or tip velocity u2, ideal, that is without consideration of slip factor, outlet relative velocity v2 dash, ideal outlet absolute velocity c2 dash, ideal outlet whirl velocity cw2 dash, outlet relative velocity v2, outlet absolute velocity cw2, outlet whirl velocity cw2, outlet axial velocity ca2, outlet blade angle with respect to radial beta 2. This is image of impeller. Direction is in clockwise, and D1H is impeller hub diameter millimeter, D1M impeller inlet mean diameter millimeter, D1 impeller inlet tip diameter millimeter, D2 impeller outlet tip diameter millimeter. N is a speed of impeller in RPM. Important information: direction rotation impeller shown as a clockwise is very important for construction of velocity triangle, and inlet velocity triangle is shown at inlet mean blade height. Note that impeller tip speed increases from root to tip diameter, and so inlet velocity triangle also changes at every point of inlet blade height. It is, as I already stated, it is not necessary to draw impeller image of for velocity triangle. However, it is shown for better understanding. Inlet mean relative velocity v1 should draw the inlet mean relative velocity in the direction of inlet mean blade angle, that is v1 is drawn with angle beta 1 in axial direction. Inlet mean relative velocity is equal to ratio of inlet actual flow meter cube per second and inlet cross section area perpendicular to inlet mean relative velocity in meter square. Inlet mean impeller tip velocity u1, inlet mean tip velocity is dependent of speed and inlet mean diameter, which has relation u1 is equal to pi d1m into n upon 60 into 1000. So draw inlet mean impeller velocity from end point of inlet mean relative velocity in the direction rotation of impeller, that is u1 is drawn from this point to this. Inlet mean absolute velocity c1, join line from a starting point of inlet mean relative velocity this is this one, to the end point of inlet mean tip velocity, this one. So this is the C1. Resultant of the inlet mean relative velocity and inlet mean impeller tip velocity is called the inlet mean absolute velocity, as flow is in axial direction, and so inlet mean absolute velocity angle with respect to axial will be 0. Inlet mean axial velocity CA1. Axial component of inlet mean absolute velocity is called the inlet mean axial velocity. Here inlet mean axial velocity is same as inlet mean absolute velocity, that is CA1 is equal to C1. As flow is in the axial direction, inlet mean axial velocity, that is CA1 is equal to C1. Inlet mean whirl velocity CW1, tangential component of inlet mean absolute velocity is called the inlet mean whirl or tangential velocity. Inlet mean whirl velocity is 0 as inlet mean absolute velocity is in axial direction. So CW1 is 0. Ideal velocity, that is for without consideration of slip factor. So ideal outlet relative velocity V2 dash, ideal outlet ideal outlet velocity is drawn here in dotted lines and actual velocity in solid line. Ideal outlet velocity is based on without consideration of slip factor, and draw ideal outlet relative velocity in the direction of outlet blade angle, that is beta 2. So ideal outlet relative velocity is equal to the ratio of outlet actual flow meter cube per second and outlet cross section area perpendicular to ideal outlet relative velocity, that is meter square. It's an outlet blade angle beta 2, which is in radial direction. Outlet impeller tip velocity U2. Outlet impeller tip velocity is dependent of speed and diameter, then it is U2 is equal to pi d2 in n upon 60 into 1000. So draw outlet impeller tip velocity from endpoint of, this is endpoint of ideal outlet relative velocity in the direction of rotation of impeller. So we draw U2. Ideal outlet absolute velocity C2 dash, join the line from the starting point of ideal outlet relativity, that is this point, to the end point of outlet impeller tip velocity, this one. So this is C2 dash. So resultant of the ideal outlet relative velocity and impeller outlet tip velocity is called the ideal outlet absolute velocity. Ideal outlet axial velocity CA2. Axial component of ideal outlet absolute velocity is called the ideal outlet axial velocity, that is CA2. Ideal outlet whirl velocity CW2 dash, tangential component of ideal outlet absolute velocity is called the ideal outlet whirl velocity, that is CW2 dash. Sleep outlet impeller tip velocity. Sleep factor is generally 0.85 to 0.90 of ideal outlet whirl velocity. Sorry, this is factor, so it should not be of this. Sleep factor is generally uh, 0.8 to 0.9 it is taken. Sleep factor is defined as a difference. Sleep velocity, like the factor is a ratio, but sleep velocity is difference. So sleep velocity defined as the difference of ideal whirl velocity minus or difference, that is actual whirl velocity. And based on the sleep factors, based on the sleep velocity is calculated, and sleep velocity 0.8 to 0.80 to 0.15 of ideal outlet whirl velocity. So sleep factor will be 0.85 to 0.9 of ideal outlet, but velocity will be difference, that is 0.10 to 0.15. So draw the outlet impeller tip velocity considering the sleep velocity. So this is the sleep. So you have to draw one more outlet impeller tip velocity considering the sleep. Outlet relative velocity V2. Join the line of a starting point of ideal outlet relative velocity, that is this point, to the starting point of impeller tip velocity considering the sleep. So you have to join this one. This will give outlet relative velocity V2. Join the line from the starting point of a outlet relative velocity, that is this one, to the end point of outlet impeller tip velocity, that is this one, drawn as consideration of slip factor. So this will give you C2. So outlet absolute velocity is the resultant of outlet relative velocity and outlet impeller tip velocity. Outlet impeller angle with respect to radial is shown as a theta 2, sorry, yes, theta, beta 2, sorry, theta 2, it is on theta 2. Outlet axial velocity CA2, axial component of outlet absolute velocity is called the outlet axial velocity. Note that outlet axial velocity is same as ideal outlet axial velocity. In both case CA2. Outlet whirl velocity CW2, tangential component of outlet absolute velocity called the outlet whirl velocity or tangential velocity. So you see CW2 is smaller than CW2 dash. Ideal and actual outlet velocity. So ideal is shown as a dotted and actual is shown as a solid. So this is ideal and this is actual. So because the slip CW2 component is lesser than CW2 dash, and that is why head rise is lowered. Inlet and outlet velocity triangle shown in different forms, either without images you can also draw this. This is inlet velocity triangle and this is outlet velocity triangle. So thank you for watching. Hope you have liked this and you understood how to draw the velocity triangle for ideal case as well as the actual case. So thank you. Thank you.